There are a whole bunch of different transitions that can emit light. We can have a transition, for example, where an electron can fall from the second shell to the first shell. I want to do this in a different color. So we can have a transition where an electron can fall from the second shell to the first shell, the third shell to the first, the fourth shell to the first, the fifth shell to the first, the sixth to the first, the seventh to the first. These energy transitions tend to be really high in energy because it's a pretty big fall and we can't really see them. They tend to be outside the visible range. These are all within the UV range because it's a really high energy change. Falling down to the first shell releases a bunch of energy. There's other transitions that are possible. Falling from the third shell to the second shell tends to release red light. Fourth to second, green. Fifth to second, blue. Sixth to second is violet. Seventh to second is no longer visible again. It's back to being UV. Then there's literally as many possibilities as there are shells. Well, actually more than that. So then we could go 4 to 3, 5 to 3, 6 to 3, 7 to 3, etc. But only 4 of these lines end up within the visible spectrum. And those 4 lines, hydrogen, again, this is just for hydrogen, will not emit orange light. It won't emit yellow light. It emits these 4 wavelengths and those 4 wavelengths only because of the energy levels of its shell. For it to emit orange light, maybe, which it doesn't, I would need it to fall from like here to here. But an electron can't be between shells, so that's not a possibility. It can only make these moves. So if we were looking at the emission spectrum of hydrogen, we would see these 4 bands on a black background. We'd still have to put it through a prism and break it apart so we could see the different waves, but we only see 4 bands of color on a black background. And this is hydrogen's signature. This is how scientists can look at stars that are bajillions of miles away and tell you what elements are there. Hydrogen has one particular signature. Helium has a different one. Compounds have different ones. And so by looking at this spectrum, we can analyze what's there. This is the emission spectrum. There is also what's known as an absorption spectrum. If I put energy into hydrogen, so it was absorbing instead, it could absorb going the other direction. It can absorb UV light to make those transitions. It can absorb red light to do this. It can absorb green light to do that, blue light to do that, absorb purple light to do that. So the absorption spectrum, it absorbed 4 colors. And so where it absorbed those 4 colors, we see 4 black bands on a full rainbow spectrum. There are 2 clarifications I would like to make here. One is based on the fact that as you get farther from the nucleus, the shells are closer together. So if we have jumps that are both one shell, for example, that jump versus that jump, the jump from 2 to 1 is larger and it's going to release more energy than this one will. So 2 jumps of the same number of shells aren't always equal because the shells are not equidistant. So a jump from 7 to 6 only releases a tiny amount of energy. So if I were comparing these 2, 4 to 2 and 3 to 2, both are jumps of 2. This one is going farther, so it releases more energy. Another possibility, I mean, there's not infinite number of possibilities, but a whole lot of possibilities. So which of these two would release more energy. That one would. Okay. I could also ask you a question, something to the effect of, of these, which one absorbs the most energy? If I'm asking for absorption, I can rule out this one and I can rule out that one because those are going to release energy. These two are both absorption. Which one absorbs more? This one. Another thing I need to clarify from a previous part of this is, and it's just because the question shows up a lot. If I were looking at the emission spectrum of hydrogen, the lines get closer and closer together as you go this way on the spectrum. This is frequently expressed on the IB exam as the lines converge, meaning come together, get closer together at high frequencies, because violet light is indeed higher frequency than red light. So the emission spectrum will reflect lines converging at a higher frequency.